Okay, so we should be live now. Can everyone hear and see me? If you can hear and see me in the chat, say hello. So is everyone here and can see me? So, oh, I didn't play the intro now. I was like, we're just going to go straight into it. Sorry about that. I clicked the button and then all of a sudden I see this red error message come up. So good to see everyone. Ivy, Joelle, Kyle, David, Joe, everybody. Mason. Let's make Mason a mod. I'm trying to recognize as many names as I can. And so we'll start talking about everything now. So the good news is you just found out how quickly I can remake everything. And so good to see everyone. Nicholas, Livia, Matthew. We're making you all mods, but that is literally the minimum amount of time I can remake the stream, get everything up and going, which is kind of good. I guess that took about 5 minutes. I kind of waited on it a little bit to see if it would fix itself. But, and then actually, you know what's funny? This is really funny here. It's so interesting, like, talking to you guys, because I feel like I'm in class again. Oh, I feel like I'm in class, where I look this way. If you see me looking this way, I'm totally seeing you guys. So, Joelle, a big thing, and check this out, everyone. Go to the bottom, there's a scroll wheel, and you can change the quality of the video. I have upgraded my Comcast all the way up to, like, super awesome Comcast, where I get... They wouldn't let me get gigabit internet. I have 600 megabit download, and I'm getting, like, 30 megs up. And so I saw Connor at the very last moment was like, make sure your bit rate's good. And we should be having a constant 5 megabits up bit rate. And I think I'm only doing 720, which needs about 2 or 3 megabits. So we should be good on all this. But go to the very bottom of your screen, like down here below. Does everyone see down here? I'm so sorry. I got a 4K camera. So does everyone see right down here? There's a scroll wheel. And that scroll wheel will let you change it from like 720 to 1080. So when I pull up things like RStudio, and so if you see me pull up RStudio and it's not clear, one, you can always ask me to increase the font size. But two, and I like it, I'm in the plot window right now. That's a good place for me to be. But you can change it. Has everyone found the little scroll button on YouTube that lets you change the quality? So you can change it from like 480 to 720 to 1080. I think we're only broadcasting in 720. But if you change it, it should be very, very clear. Everyone good on that? Everyone doing great? A bunch of big things right now. We should release test grades later tonight. So we're going to post test grades. If you haven't taken the test, talk to me. I think there's at least 2 people who haven't taken it. I'm trying to think what other big news there is. So try to remember all the names. So well, there you go. So all the mods can see everything. So way more clear. Me laughing. Yeah. So unless we know someone is a troll or something like that, don't worry. And that's what the mods are for. So good job, mods. So and then don't block anyone unless we know. And if you were blocked and mods in action, it's 474 right now, Julio. But feel free to enjoy and watch, Julio. So good to see you. And so we're doing some 474 live on YouTube. So what do we have going on right now? And I want to say this. I think I can say this. If this is true or not, professional baseball teams are using R. Like R is something that is used throughout multiple industries. I've said that 1,000 times, but R is a very utilized program. The knowledge in it is very important. It's really good stuff that we're learning and knowing how to actually program and everything. Like programming is a huge skill set. So thank you everyone for being here. We've got almost all the class here, it looks like. So awesome stuff. Oh my gosh. This makes my day. Every team uses R from a reliable source right there. Collect and analyze data. So that is the big thing. And we'll get started here. So feel free, Julio. You know what's funny is we're going to talk about some stuff today. Let me go over to the notes. We're going to talk about regression. So music, I love it. And feel free in the chat to talk to each other. You guys know how it is, just don't be like, Brian's an idiot. I mean, I don't know why people would say that. And of course, I can see your name if you say that. But feel free to talk to each other. I can see everything. It's kind of a fluid conversation. This is streaming. So I hope you guys are enjoying a lot of the new online formats your class have. But in this class, especially here, I want everyone to just say hey to someone by tagging them in the chat. So if you saw someone talking, I want you to type an @ symbol and type their name. Like I'm going to say hey to Aaron. I'm going to say hey, Aaron. and then I've tagged him in the chat, and his name will be highlighted. And so there we go. We got people saying hey in the chat. So say hey to someone. Get 10,000 points if you say hey to someone. This is how we run the online class right here. People saying hey in the chat to each other. You can tag someone. You can ask them a question. Say hey to someone. All this great stuff right here. So I want you guys to enjoy this. I want you to realize that this is not me just reading notes to you guys, because we're going to go through notes. Hey, but we are actually going to interact, and you guys are going to talk to me, ask questions when you have them. Mason, we need to make you a mod here. So make Mason mod. There we go. So we got everyone saying hey to each other. Awesome stuff. So good to see everyone here. We got people saying hey to me. And do you notice how your name, don't wait. Wait. Don't post links. Don't post links. You can remove your comment. So don't. I don't know what that link is to. So there we go. Awesome. So all this good stuff right here. So glad to see everyone. Saeed likes Kyle's hair. So Calzone Tyrone, man, we need him back. He's a stat to one staple. Maybe we'll see him swing by. He's a mod, so when he comes in the door, everyone will know. Well, you'll see his name, but he was a student from New York who just happened to stumble upon our channel when we were doing a Kahoot. He joined in, had tons of fun with us, and at the end we decided to make him a mod because he was such a nice guy and was just playing along. So we were like, hey, you're a mod now. And he really liked it. He was a really great guy. So it was so cool. Like some of the students like found him on Instagram and stuff. I don't know. People were just like talking to him and having a great time. But he's a staple of the channel now, Calzone Tyrone. Okay, so we understand how this works, how to say hey to each other. And I think my volumes are good and everything. If my volumes ever get weird, if I ever get too loud, just tell me. But I can look at everything and see how it's going. We're trying to get some new equipment too to make it even better. And maybe one of these days I'll have my green screen back and, it'll be cool again. Okay, you guys ready to learn some statistics? Some regression. Mike sounds perfect. That is awesome. Yeah, we're using the Shure SMB9 or 7, excuse me, Shure SMB7. I shouldn't move it. I shouldn't touch it. I just bumped the cloud lifter. So you guys are awesome in the chat. So when I'm generally, I've got the notes there, so you'll see when I'm looking at everything. I'm going to try to, unfortunately, I was trying to, before class, make it so I could write on the notes, but the notes when they're in PowerPoint look like this, and you're not going to be able to read that. So I didn't, because in this, I can actually like write on it, but we're not using that. We're not doing that. That's not readable. If you can't read anything, please tell me. If at any moment you're like, Brian, the screen's not clear enough, it's not large enough, please tell me. We'll fix it. I want everything to be readable and easy to understand. Okay, let's start talking about this here. Let's get into these notes. Okay. So when it comes to what we're doing, we have two big concepts right here. And I think I can highlight still. Let me find my highlighter. I'm not used to this version of it. Is this highlighter? That's drawing. Oh, but then it does that. We've got descriptive and predictive analytics. I want everyone in the chat right now to tell me how descriptive analytics work. I want someone to give an example of descriptive analytics, like 10,000 points right now. This is your practice, and we'll be augmenting these exams. So I'm going to try to keep to the questions I asked during lecture, but I want you in the chat to be writing an example of a descriptive statistic. Like, what is a descriptive statistic? What do we mean by descriptive statistics? There's got to be kind of, like in the past. That's great, Joel. 10,000 points right there. Tells us what, does it say that? Does it say like what's been going on in the past? It's like I know my definitions of them, and then I don't always read what like the book says because I've like been doing this for so long and learned it like in 3 different classes. Model of our art. John, that's an amazing answer right there. Model of our already collected data. Exactly. That is some really great stuff right there. How well did a batter hit overall in the last season? Exactly. Average income by state in 2015. Exactly. These are amazing answers. 10,000 points. If you're answering questions, you get 10,000 points per answer. A player had an RBI of 300 last season. You bet. These are amazing answers, and they're all descriptive statistics. And I kind of like that. I might start using that. Like, tells us what happened in the past. Now, multiple regression is a tool. So 10,000 K right there is a tool to do descriptive statistics, or we could do predictive with it. Because you could use a multiple regression model. I can't do as pretty of drawings in this layout right here. Oh, maybe I can. Maybe I shouldn't knock Adobe Acrobat. So this is a simple regression. Ooh, It's not how regression really looks. We want just dots, not lines. But with a regression right here, you can make predictions or you could describe. So regression regression leads to multiple regression. So when we talk about predictive analytics, we can use the line to predict new observations, or we can use it to describe data we already have. Like maybe that line describes the data we have, or that line can be used to predict for future players. So when you do predictive and describes what has already happened, exactly. Great answers in the chat. You should automatically know descriptive and predictive analytics. And then we have prescriptive analytics, which isn't on here, but prescriptive, I know video chat is awesome. Prescriptive analytics is when we try to come up with a solution like, how can we improve this player? What football player is the most valuable in 2022? Exactly. That is predictive analytics. And then how do we improve our players, or what is the best way to draft for us would be prescriptive analytics. Like, who do we draft and why? Who do we draft and why would be prescriptive. Which players would be the best is predictive. And then who do we draft and why? So you can make a model that kind of predicts who you should get based on your team and all these things, and it would give you a prescription. Think about that. Like, a prescription tells you what to do. It's a pathway. So when you talk about prescriptive analytics, you're making a prescription using statistics. It's kind of the end-all be-all. With the free agent data we went, that's exactly right. Aaron, you are right. 10,000 points, Joel and Aaron. So we get into some really huge stuff right here. Probably the biggest thing right now is you have to know the bias variance trade-off. So when it comes to the bias variance trade-off, you have to know first what bias means, and you have to know what variance means. I think everyone knows what a trade-off means. A trade-off is pretty easy to understand, that if you increase one, you'll increase another. So the bias variance trade-off. Bias is simply understood as how good or bad your model does. A model with low bias will be very, very accurate on the data it was created from. That's probably the best definition of bias I can give you. A low bias model will be very accurate on the data the model was created from. It'll make like super awesome predictions. And that looks really good. But then variance probably goes up. If bias goes down, variance probably goes up. That's the bias variance trade-off, is that when you decrease one, you increase the other. It's not like on purpose. It's just the way it goes. It's just how models work. So what is variance? Variance is related to how much information we extract from the data. Now, just go with this is so funny because it's what I did when I first did statistics. I took all my variables, and what do you think I did with all my variables? 100,000 points. Oh, we got a screen for this. You guys don't know about these things right now that I got, and I'll be making more things. 100,000 points. It's a random 100,000 points. Tell me, what did Brian do with all his variables? You've probably seen me do this before. John knows exactly what I did. I threw them all in the model. So what is my model going to do? Imagine, Livia got to, so we put all the variables in the model. Matthew, I'm giving you 100,000 for taking a shot at it. I love when people give answers. And Connor knows the analogy. I took all of them and I took all the information out of them. Imagine each of my variable is an orange, and I just made some orange juice out of it. And so I took all my variables and just squeezed all my variables and took all the information from every one of my variables. Now, how much is my model learning right now? How much information is my model taking in? It's taking in a ton of information. My model is taking in just gobs and gobs and gobs and gobs and gobs of information. So with that, it's taken in all of it. And the problem is that when my model takes in so much information, it becomes information dependent and too much maybe. And how would we know, I'm not going to hit the button, but another 100,000 points. How would we know if my model's taken in too much information? How would we know if my model's taken in too much information? How could we possibly tell if my model's good or not? This is something you should know pretty quickly and pretty well with predictive analytics to know, there we go, we got overfitting right there. If my model is overfit, adjusted R squared's kind of good. All these things right, and everyone's kind of right. But the overfitting is a big, and there, Livia mentions it too, but it doesn't track on new data. The model's probably overfit to the data it was originally made on and doesn't generalize well to new data. And this is the biggest thing for predictive modeling. I can't stress it enough. In predictive modeling, it's all about how does it work on new data. So you could be right. We could look at the adjusted R squared or the R squared, but remember, it's all about how it works on new data, which is the holdout data. It's so important that you don't forget holdout data. Like, I don't want to fail people, but if we do predictive modeling and you're not using holdout data, you're doing it completely wrong, because then you're not seeing if your model actually works on new data, which is the whole point of predictive modeling, to see if you can predict on new data. So the bias variance trade-off is so key. If you have questions at any point, feel free to ask. I still don't understand what bias is. Bias would be things like your RMSE, which is your typical miss the model makes. A low bias model would have a very high R squared because it explains a bunch of the data. And our R squared is related to how well the points fit around the line. It's hard for me to show what's going on right there. Variance is related to how many X's are in your model. Like the more X's you put in, the higher variance, because you're extracting more information. So what else do we have right here? How each model works at the fundamental levels described by a layperson. Good stuff. What assumptions, if any, go into making it, like linearity? What types of relationships are well suited? And here's a big one. What parameters can we tweak in a model to potentially make it perform better? So you're going to see stuff in these lectures about bias variance trade-off, and we have what are called tuning parameters. So take a big note right now about tuning parameters. Lambda and alpha. Those are tuning parameters. So when you see what parameters can we tweak, we're literally talking about tuning parameters. Is a typical good rule of thumb, and more variables you put in the model, the variance will go up and the bias will go down? 100,000 points. That's a perfect note right there. It is a typical good rule of thumb that the more variables you put in the model, the variance will go up because you're extracting more information. So your model's learning more from the data it's created from, which you would think is a good thing, because it makes the bias go down. But then it's becoming more dependent on the variables it's created from, which means it probably works on that data set. The data it's created from creates the variables, so it's learning from the data, and the more it learns that data, the more it might overfit to that data. Does that make sense, Will? That the more it learns from the data you put into the model, the more it might only work for the data you put into the model. So if you memorize that data too well, you've overfit to the data your model was created from, and it can't predict on new data. Once again, 10,000 points right here. What is the least? There's two technically. What is the least, and you'll hear about it later today, what is the least overfit model there is? 10,000 points right there. What is the least overfit model there is? I guess you can there's at least two I can think of. One we haven't told you yet. The naive, Spencer, coming in. Spencer, you have earned a mod for that right there. Spencer jumped in. He's hiding out to say the naive model. You got it, Spencer. Great job. It's so good seeing everyone. Please continue to chat and everything. So I'm trying to add in as many people as we see right here and adding you guys as mods. So you are right. It is the naive model. The naive model, and we'll see some stuff later today about how it works, especially with categorical variables. But the naive model would predict the mean of y, or it would predict everything is the majority level of y. So, my gosh, huge note right here. I think we've covered all this right here. One thing to note about logistic regression, a huge note you must know. Logistic regression is when we are predicting a categorical y. So what you get... Let me think, I got more room on this slide right here. It generally looks, it changed to looking good. A logistic regression kind of looks like that right there, because you'll have a y variable. This is why I want my PowerPoint. You'll have a y variable, and we'll predict the probability of y. I can draw way better in PowerPoint, which maybe, you know what? We might go over here, and we might just put in a slide, or you know what? We've always got Word. So it's way easier to draw in Word. So logistic regression looks like this. You've got a y, you've got an x, and then simple logistic goes like this. And what you're doing here is predicting a probability. So we can think of some really easy examples of logistic. Always try to keep a simple example of these concepts in your mind. So let's go here and predict, let's say, probability A. And so let's say, and the test grades should be released later today. I've been working on them. We're curving them. So get ready. Test grades will be coming out, and you'll see a curve on them. And then let's go here. So we've got probability in A and hours studied for test. what do you think happens to the probability of an A the more you study for a test? How big? So, what do you think happens to the probability of an A? And if you notice some interesting stuff right here, it must be bound. So, probability of an A is kind of quantitative. Yeah, I'm pretty happy with them. You guys did really well. You guys worked really hard. It goes up, it's positive. The more you study, the better the grades. And that's what we see right here. So remember, getting an A and not getting an A is a what kind of variable. Like getting an A is a what type of variable. Like if you get an A, that is a what type of variable. This is huge to it, to your understanding of it. That getting an A must be a what type of variable to use logistic regression. It must be categorical. Getting an A is categorical. So then we're going to predict the probability of getting an A. And so let's just talk really quick here about simple regression, because this is where the slides are going. And so I'll hop back to slides here in a moment. But the equation for this is E raised to the regression equation and I always have to think because I can do some checks in my head. And this is just simple regression, but if you want to make it multiple regression, all you have to do is just call this x1 and then call this like the second x in the model. So now it's a multiple logistic regression, and you just have to know the equation of the regression line. So the equation of the regression line is just this right here. So it's e raised to the over 1 plus e raised to the. And you can do some checks on this. Let's just think here really quickly on this, because I've done this with all my classes. When you use that regression equation right here, I want you to think of a few examples. If we raise e to infinity, what does that equation become? Like if we do e raised to infinity over 1 plus e raised to infinity. So if we do e raised to infinity over 1 plus e raised to infinity, what does that become? 100,000 points. First person to tell me. What does that approach? It approaches 1. Nice job, Will, right there. It approaches 1. So remember, because it'll be infinity over infinity. So it'll basically e raised to infinity is infinity over 1 plus infinity. So it approaches 1. And then we go e, here's a weird one. What does this equal? If it's equal to 0, what does the equation become? If it's equal to 0, 100,000 points first person, I'll say your name when you get it. What does it become if it's e raised to 0? It's 1/2. And then last but not least, you might notice, so we got just enough room on here, if it's e raised to negative infinity over 1 plus e to negative infinity, what does that become? What does that become? 0. Nice job, David, right there. And look, we just covered every single number, and look what it's contained between, is that all these probabilities must be between 0 and 1. So you'll notice that with doing this right here, it approaches 0, all these great answers. And so you are right, it never truly becomes it, because infinity is just a concept. Infinity doesn't actually exist. But we see how the logistic regression works. This is the equation for it. Let me highlight it nice in here so you can see it. We got Space Pen back. Everyone loves Space Pen. So we've got the equation being used. And really the truth is we don't usually write it out. Like that's the thing about statistics that people don't understand is you're not sitting around solving equations. You just have to know how they work. You have to understand that logistic regression is used to predict categorical variables. You receive a probability of between 0 and 1, and it can be multiple logistic if you add in multiple x's. Those are the key concepts you should understand about logistic regression. You should pretty much know them like that. So have those notes. These reviews we just did right here are key, and they go through the concepts in the slides. So all this stuff right here, tweaking the variables. We've got review right here. So if you see me do this quickly, it's because we've talked about it a lot. We were talking about this earlier, generalization error. This is estimated by the k-fold cross-validation, but the generalization error is how it works on completely new data. Training data, and what do I mean by new data? Generally, we use a holdout data set to see how it works on data the model has not seen. We take some of our data and we break it off and we say, okay, this data over here will not create the model. This data right here is going to create the model, hence it's called training data. So the training data creates the model. And then there's something in between. 10,000 points, who knows what's in between the training and the holdout? It's kind of mentioned up above. What is in between the training and the holdout data? What is in between it? Before we do the holdout, we have to get something. Validation. David, you are right. The validation data is the k-fold cross-validation. John right there also. Keep answering if you haven't answered. Shows you're involved, and I like it. 10,000 points if you give the answers. And so keep it up, Christian. Thank you so much. We see right here that we have training is what we create our model on. Validation is within the training. We've seen the slides. Ask questions if you have it, but we'll show it again here. We're all getting our brains back into doing statistics right here. But the way validation works is you literally have, if you're doing k-fold 4, you put 4 folds, and this is holdout. Just write hold on it. And then when you do it, this would be your validation, and these would be your training data. And when you make your estimates of how your model works, you create your model from this, and then you test it on this. But the reason it's called k-fold validation is you move through the validation, and the next time you do it, because you're going to get 4 estimates of how your model works, is you create your model from this, and then you test it, and that's just one model being created. You create your model from the training, and then you test it on the validation with using certain variables in the model. So the validation moves throughout. So you literally do the k-fold process. If it's k-fold 4, you have to get 4 estimates, and that kind of gives you an average of how it works. So now we get training, 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 and validation here. And then, of course, these will test on this. Like, that's one model being created. It's not 2 models. It's just I can't draw over it. And then last but not least, you test on that validation, or you validate on it, and then you train on these, and then you go here, and then these give you the estimates of how it works. And then after you choose your best model based on these estimates, you take your best model and you do it one time on the holdout. If you notice, I wasn't dealing with that holdout till the very, 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 very end of it. The holdout is not used till the last moment. How many times should you be testing your model on a holdout? How many times should you be testing your model on your holdout? 10,000 points, who knows in the chat? How many times should you be testing your model on the holdout? Should you be? 1, John is right. Just 1 time. You just want to test your model on the holdout 1 time. Now, you can go back to the drawing board and create more models, but the goal here is that we test our model 1 time and only 1 time on the holdout. The validation is used to kind of create our models and to look through and to say, like, okay, how do these models work? And it gives us an estimate. So it's key to know that we call this the estimated generalization. That's how we estimate it'll generalize, and this is how it actually generalizes. Because holdout is new data, validation is used to estimate how it'll work. Validation is used throughout the k-fold cross-validation process, and it's in different spots, so it actually makes the model at some points. Hopefully that helps everyone better understand. And here we are right here. So we've got overfitting. Overfitting is when our model has too low bias. We put way too many variables in the model and it doesn't generalize well to new data. So overfitting is a problem of low bias models. The naive is the least overfit model there is. We talked about that a little bit. Easy stuff right here. Once again, if I go through a slide quickly, it's because I'm like, okay, this is very easy information. But we've got response versus predictors. It's so awesome. A 2-1 student was asking about this yesterday because the response is the Y. And then you can call it a feature or an X variable is just an explanatory variable. I like to call them explanatory variables, but we have to figure out predictors to put in our model, and we have to have a Y. Now, I can't say it enough that in logistic, we are doing categorical variables, but we will predict the probability of it being a certain level. So when you see something like junk mail, junk versus safe mail, we will be predicting the probability, and you always have to remember, my brain's even breaking right now. Truthfully, it's funny because some software I've seen do it differently, but inside of R, the level of interest, so what is it? My brain is like, it's like, remember. So, because if you get it wrong, it's completely wrong. But there's there's always a way to know you're doing it correctly. Let me show you the way to know you're doing it correctly, which I always check. So whenever I'm doing predictions, it's when you get predictions, your axis right here, logistic last, that's what it is. It's logistic last. I just remember in logistic, the level of interest is last. So there we go. My brain was like, I have a saying for this. Because you know how I make you guys remember sayings? I remember the sayings too. They help me. Because there's no reason. In logistic, the level of interest is last. So if we are predicting if someone's going to make an A, yes or no, what will we be predicting? It's yes or no predicting someone makes an A. Will we predict yes or no? Like, what will we predict the probability of? Yes or no? So which will we predict? Yes. Yep. So this will say prob yes. Yep. So we are going, it's because it's logistic last. In logistic, the level of interest is last. Does everyone here, like, let's put this in the chat right here. It's a good way to remember it. I had to remember it. Logistic. So logistic, oops, got caps. 6, level of interest last. Do you see the L's right there? Logistic level of interest last. So the level of interest means the one you're predicting. So it's last alphabetical, and indicators are first. So I am first. That's the way I remember that one. In indicators, all the indicators are first. So the non-indicator is, no, in indicators, the reference level is first. So many things. So logistic, yeah, and we don't use, at least the way R programs it, it's not going to be no. In logistic, the level of interest is last. In logistic, the level of interest is last. Yep, but remember, logistic level of interest last. So the level of interest is the one we're going to predict for. Does that make sense to everybody right there? Because Y is, it's the second to last letter, if I'm doing it right in my head. Logistic level of interest is last. So, and we could do some really quick stuff on this right here. Let's do it really quick. You can always do a test of it. So let's pull up R right here. Let's open a new R script. And we should have all of our stuff in here. Hey, I don't have to reinstall stuff because I'm on my computer now. So we're going to pull up a reg class right here, and we're just going to make a model. And we're just going to do it the old way right here where we do a linear model, but Petri has it programmed in this way. We're going to do survey 10 because I always use survey 10. Survey 10, and we are going to predict, I think it's just gender in here, and then we're going to do it by weight, and then data equals survey 10, family equals, and we need binomial. I think that works if we put in quotes. Okay, it looked good. It's looking all right there. Let's go to visualize model. It worked. Whoa. Oh yeah, Petri said he updated this. Whoa, he put in the 50% probability line. Did he tell me he did that? If you notice his probability of male on here, and he added that in. So we have male and female as the two levels of this variable. And so if you notice, as weight goes up, the probability of male goes up. So we have here a logistic model, and that's what it looks like. It looks just like the one I was drawing as a theoretical one. And so you should kind of know these concepts in the background. Like, these are the things you should know about logistic. Like, when do we use logistic? I promise you, employers have asked possible students to be like, when would you use logistic regression? You'd be like, well, when I want to predict the categorical variable, and we know it kind of has a consistent probability unless we add in interactions. There's a lot to know about it. So let's continue on with learning more right here. Okay, so here we are with our different types of models we can use. This slide is kind of a reference slide, so I'm not going to stay on it long, but wow, there's so many things we can do. And we will at the end start talking about neural nets and support vector machines. But if you notice right here, we've got linear and logistic regression. There is multinomial logistic. We don't really get into that in this class, but you can predict multiple class levels. It's really good packages in R. We've got decision trees, so all this great stuff, but this is tons of different predictive analytics we can do. Here is a huge slide. I can't state this enough. This slide is huge. You need to take a note right now. You need to know everything on this slide instantaneously. So what's going on right here? We've got the misclassification rate of a model. Everything right here is for categorical variables. When I run plot on M, I think I know what you mean by that. Are you saying this right here? Because this right here runs a lot of code. This right here runs all this code right here. If you're asking that, is that these slides are posted? They're at the very, very top section. So you'll see these slides at the very top. Oh, plot instead of visualize? Oh. Probably, I think when you run plot instead of visualize, it does different things for the model. It does like the residual plots. Yeah, it's going to do different plots. Ooh. Yeah, it gives you, you guys can see what I'm saying. It gives you like the Cook's D. It gives you the influence plots. I don't know if it knows how to handle it properly. That's base R right there, and base R does not look to know how to handle it properly. So base R does not look to be handling it properly. So use something like Dr. Petrie's visualize model, and that will do a great job because base R is not really knowing how to handleize logistic properly. So good stuff right there. So here is the big slide counter, 10,000 points. Great question. With classification, what kind of variable are we dealing with? 10,000 points. You have to tell me. You have to know this immediately when you see this. It's like these small things right here are so small, but you need to know it. Yes, timestamp. If you guys want to send me timestamps or stuff, tell me because this is huge. Categorical. Julio, 100,000 points right there. You are right. That is all categorical. Julio's just jumping in, grabbing those points. You are right. This is categorical. And misclassification is how often we get things right or wrong. Imagine you're trying to predict if someone will be an all-star. So misclassification is how often you get it wrong. And then accuracy is just the complement, throwing some 201 words in right now. Accuracy is just the complement of misclassification. But we get to a super complicated one. And yep, and we're going to see the confusion matrix right over here. There's the false positive, false negative rates. So the confusion matrix can get us the false positive, false negative rate. And then AUC, this is a concept that we reviewed in class, and I'll probably be reviewing it in more videos. I might even make a video going over AUC. AUC stands for area under the ROC curve. So let's just do a quick thing on it right here again, put it in this video just so we can see what it looks like. Oops, there we go. Gotta hit Control N, get the new graph. So when you draw the AUC curve, it actually took me a while to kind of completely understand this, is a large AUC is better. So what you want, you've got this line in the middle, and you want a large AUC. The larger the AUC is better. This is think of it as a 1x1 grid. What is the total area for a 1x1 block? What is the total area for a 1x1 block? Like what is its total space on a 1x1 block? The total space would be 1. 1 squared. There we go. Nice job, John. You're all right. That's the math. 10,000 points, John, right there. It'd be 1. The total area under here is 1. So what you want is you want an AUC curve that looks like this. That is the best AUC curve because the area under the AUC curve is 100%. 100% of the area is under the curve. You don't want an AUC curve that goes something like, this might be an AUC of what? Can someone guess what this AUC is? What would that AUC be there? I like that 0.55, 0.6 something, or yeah, exactly. That's not a good AUC. So what does this all mean? We've talked about this a lot. We talked about it a lot before break. And remember, a decimal, everyone 10,000 points. Remember, it's a decimal. It's always between 0 and 1. So when you think about what this means, you've got down here, you've got right here true positives, I believe. And this is false positives. Okay. So I want you just to think conceptually about this, because if anyone asked you to explain AUC, you'd want to be able to say, like, what does it mean? A curve like this would mean how much of your false positives do you have to go through to get all the true positives? How much of your false positives do you have to go through to get all your true positives? What amount of false positives do you get to get all your true positives? Like if you're trying to predict if somebody will buy a house, You want to predict accurately that someone will buy a house. So how many of your false positives do you have to go through to get all your true positives? A very small number, close to 0. So that means you get about 0 false positives and you capture all your true positives. That's what's really great right here. A curve like this is pretty much just a random chance curve, and I'm trying to draw on it right here. That curve right there, how much of your data, how much of your false positives do you have to go through to get all your true positives? How much of your false positives do you have to go through to get all your true positives? Like to find all the people who are going to buy houses, how many people do you have to go through? And the answer is all of them. Because you only reach the total true positives when you get to pretty much through the whole data. So you'd have to go through all of them. Because at this point right here, when the curve reaches the top, you've gotten all your true positives, which means you've found all the people who are going to buy houses. But you had to go through tons of false positives. You had to go through like tons of data that are not buying houses. Does this help make the concept make a little more sense right here with the true positive, false positive on the chart? It's really important. And you can see a good, like when we look at probabilities right here, if we give things probabilities, this is an example over here to the side where we have here 100% and we have down here 0%. So the way this works when we do data is if you had things like, we'll say yes, 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 no, yes, no. And if you had something like no, no, yes, 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 yes. Now, when you look at this right here, sorry, the last yes is off the screen. When you look at this right here, the first one is going to have a better AUC because you only have to go through this much of the data, where this one you have to go through all of the data. You also hit more false positives up there than you hit with this one. Kappa, we're going to do that next. Kappa's a fun one. I'll just explain what Kappa is. Okay, so what is Kappa? Kappa, we will not compute, but you should have just kind of a decent understanding of it. So when you look at Kappa, make sure I get the equation right. The equation for Kappa is going to be, I'm remembering in my head right now, it's one way of writing right here. And then what is the top of it again? Yes. Okay. There we go. Okay. So what is Kappa? Kappa kind of maxes out at 1. A Kappa of 1 is super awesome because that means you have an accuracy of 1. So what is the best accuracy your model can have? The best accuracy your model can have is 100%. So this could be 100%. Your model could be 100% accurate. But what are we talking about here when we talk about the guess model? Yep. And so, but it's also, usually they say you want Kappas above like 0.8. I don't love Kappa. It's not my favorite, but it's on the notes and we should explain what it is. So what we have right here is that we compare it to how the model would do if it was doing random guesses. And what do I mean by random guesses? If we were to say like 55% of the students are male, what would you guess, everybody? And this is a really good review of the naive model. If 55% of the students are male, what would you guess every student to be? If 55% of students are male, you'd guess every student is male. So you'd guess, I mean, I think I said it properly. So you would go right here and you would say, well, we would put, I guess I should put that as a decimal. And then you compare the accuracy of your model. And then the accuracy of your model might be like 80%. So this is how, so 80% in this example is the accuracy of my model. My model had an accuracy of 80% of predicting someone's gender. Now, the kind of random guess model would have 55% because 55% of students are male, so it would guess everybody's male. And then we compare this to how far it is from a perfect model. So it's really kind of like a ratio when you think about this, and we should always try to put it conceptually in our head, that Kappa is just a ratio of our model to perfect model. But here's the thing. the way the perfect model is compared is also compared to a random guess model. So it's our model compared to random guess, perfect model compared to random guess. But we're really just kind of, when you think about it, we're looking at how our model works and how the perfect model works, and then we're looking at a ratio. It's kind of how close is our model to perfect, but it's weighted by how far away it is from the guess model. Does that kind of make sense right there? Like, it's a comparison of our model on top to a guess model, and on bottom it's the perfect model, which has 100% perfect, like a theoretical perfect model. We don't have that model, but if a perfect model existed, it would be 100% accurate. And then we compare that to the guess model. So it's just two comparisons right here. Our model to the guess model and the ratio of that, of the perfect model to the guess model. So does that all make sense right here with Kappa? I think that's probably the best way to understand it. I know a lot of people teach it a lot of different ways, but I've always kind of resonated with this way. So that is what Kappa is. And that kind of completes this slide for the top part. So those are, you should know every one of those. Like, we could do a selecting a definition thing on the test, because we're going to do multiple choice and stuff like that. So expect to see like selecting what is the right definition, all this good stuff right here. RMSE. RMSE is the typical miss a model makes. You should know that. R squared, the percent of variation in the Y explained by the X. I have a big pet peeve. 100,000 points, and maybe Julio might know this if he's still watching. R squared is not this. R squared is not this. 100,000 points. R squared is not this. You got to say it in the chat. I don't think anyone in our class will do it. Yes, Julio knows it well. I hit the random button. I hit it again. R squared is not correlation. R squared is not correlation. My 201ers know that. And I saw, and it's all right if a 201 watch it, it's all right. But I had a bunch of people writing things about correlation. Well, what is going on? I had a bunch of people writing things weird. I had a bunch of people writing things about R squared being correlation. And I was like, no, it's not correlation. R squared is not correlation. R squared is the percent of variation in Y explained by the X variables. So don't worry. I just think everyone learns. We learn R first, and we learn R squared. So then they're like, if we square root, and then we learn if you square root it, you get correlation. But a lot of times you can't square root it to get correlation because it's not a single variable thing. MAE, we don't talk about that much, but you should know it. MAE is just another version of RMSE. I'm sure if you went to another school, they might be like, don't use RMSE, use MAE. Tomato, tomato. It's RMSE is going to do a stronger weighting towards outliers. 100,000 points in the chat. Why will RMSE give a stronger value to outliers? That's a good theoretical question. Why will RMSE upweight outliers in your model, or things with high residuals? Why will RMSE give a stronger input out? If you're trying to reduce the smallest shows there. Yes, Connor, that is a perfect answer. I don't know if you looked that up, but that's perfect. RMSE is going to square them. When you think about root mean squared error, so since we're squaring the error, because both of them stand for mean absolute error or root mean squared error, because if you square an error, that makes it bigger. We are going to root it, but we're going to average together all the... Sure, why not? That was an excellent answer. So RMSE is going to give more weight to outliers. And thank you, everyone, for all the chat. Yeah, that was a complex one. Yeah, we learned a bunch of great stuff right here. Here's all the definitions, a measure of the accuracy of the model relative to the accuracy of random guess model, all this good stuff right here. So if you need the definitions without me saying them, there they are. Transformations, most algorithms work better with roughly symmetric. Remember, we need to scale and transform stuff. We usually want things to be roughly symmetric, pretty much normal. So we need to make data pretty normal. That's all this slide is talking about right here. A big thing with our algorithms is normal data, because, and like your test said, if you have algorithms or if you use variables that are not normal, then one variable might have undue influence on the model. So I think we saw examples like with like shoe size and salary. So if you input salary, it's going to be really weighted towards salary. So you have to watch out, because your model might try to like make a model based on one variable, but you want all variables to have equal say. So here we are with the task of classification. And once again, we've been reviewing this the whole time. So if I go a little quickly, tell me to slow down. But classification is all about class labels. That literally just means we have yes, we have no, we have junk, we have spam. We're just trying to label something. We're just trying to label something in a class and say if that class is accurate. That is all we are trying to do. We're trying to see if people donate or if they don't donate. That's what class labels are. So hopefully everyone knows that right there. But you should know that. So here's more examples. So with this right here, we're going to go to the big slides. Probability, and this is something we talk about in statistics a lot. Probability is the long run probability. And I think this blows people's minds because we're not talking about, like, let's say someone says, I saw some stuff about poker earlier. Let's say someone says, I win 30% of my poker games. This would be pretty good. If you're playing at like a 5-person table, that'd be amazing. Now you got to make sure you're not winning like just the antes. But if someone said I win 30% of my poker games, someone give me a good definition. I wish we could just put this as a test question, have you write it out. But someone give me a good definition of what that means via this slide. Like, what does it mean to win 30% of your poker games? Like, what does it mean to win 30% of your poker games? What does that mean? Use the definition up here to kind of think of what does it mean in statistics to say I win 30% of my poker games. Does it mean when you sit down at one game, you have a 30% chance of winning it? Hint, it does not mean that. So what does it mean to say I win 30% of my poker games? Any ideas? Oh no. You played kind of. I'm giving it Aaron 10,000 points for that. Kind of. It's in the long run, and we kind of mean as it approaches infinity. It's an even longer run. So it wouldn't be just like 100 games. It means like a very theoretical long runs. The probability of winning, and it means like in the long run. So like if you say someone is a 300 baseball hitter, then it means in the long run, not like when they go up to bat this time, they have a 30% chance of hitting the ball. As it reaches like, as you go to like a long observation. So if someone is a 300 baseball hitter, then in the long run, you would see them like, if you watch them for like 100,000, I know everyone's saying 100, I was like, not 100, but like, it means like a theoretical long run, like a very long run. So you'd be like, oh, but I saw them miss 3 in a row. I thought they should at least get one of those. Like, well, it needs to be the long run. Yep. It moves towards 50% in the long run. Exactly. It's the law of large numbers from 201. This is literally the law of large numbers. So it's cool, so cool to see concepts coming back right here. And you see it right here. You see the law of large numbers in action, that if we have the probability of getting a 7, well, you would think it'd be 1/7 or it'd be 1/10. It's drawing a 7 here. And at first we see 0. And then at the end we see close to about 30%. But in the long run, in the very, very long run, what do we see? This is the law of large numbers. The law of large numbers states that we will see the true probability in the long run. I love it. I love seeing everyone in here in the chats. I do not know why every time I try to go forward, it's telling me like, I do not like using this. I want to use, there we go. So probabilities, once again, these are easier concepts. I stop on the harder concepts. Probability of 0 is impossible. I always say like that's the probability of me meeting Deadpool, because it's so sad right here. That's good. I'm glad he's teaching it too. So probability of 0 is impossible, like me meeting Deadpool. And then, you know, like death and taxes have a probability of 1. Fun stuff right there. And so 1 means it's going to occur. And we have things like the complement. So you either make a purchase or you don't make a purchase. So the probability of making a purchase is 70%. The probability of not making a purchase is 30%. Probability of clicking, not clicking is 0.99. The probability of clicking is 0.001. As I tell my 201 students all the time, we use these concepts that they learn in 201 repeatedly throughout statistics. So it's just building that knowledge from the ground level up, just stacking new things on top of it. Because there's the complement, there's the rules of probability, things we've learned many times. Why you do this, computer? Maybe it thinks I'm over there. So weird. I swear I know how to use a computer. It was doing it earlier. Oh, it like wants me to put in a note. That's what it's saying over there. Sorry, everybody, for the little delay right here. Let me close out the notes section. And now not. Okay. So maybe drawing might not work. We'll find out. So we have right here, the philosophy of business can be summed up as information matters. Once new information is available for a problem, strategies may change. Yeah, so really, this is just a conceptual slide right here, where we're just talking about how do we handle information from businesses and what do we do, all that great stuff. Boom, we're on to some big stuff now. Okay, so now we're into the prior and posterior probabilities. This is very important to know what a prior probability is. A prior is just your baseline probability of something. We might know that 6% of our donors donate, 6% of our alumni donate. That is a prior probability. It's kind of just like the naive model. It's just starting out a base point. You notice how it says marginal probability? This means just if you look in the margins, and let's draw it right here, and this will be a really good review, especially for homework problems. People were asking about this yesterday. So, I thought I might still, do I still have it up? Closed out some stuff. Looks like I closed it out from yesterday. So here we are. So if we have donate, yes. So we have actual and we have predicted up here. And let's go here and put 90, 50, and then 20 and 40. Here's some key questions, and this will help you out for the homework assignment. A few people were stuck on this. What is the accuracy of this model? I'm going to start filling it out. Try to solve this right now. 100,000 points, first person to tell me what is the accuracy of this model. The A stands for actual, and the P stands for predicted. 100,000 points, Joel. Thank you for asking. A stands for what someone actually did, and P stands for predicted. 100,000 points for also people answering in the chat. Thank you, everyone, so much. I love all the questions, and I love the answering. So we go right here, and if you notice, so I'm going to write some more numbers. People are saying the answers in the chat. Great job. And then I'll start highlighting stuff to show what's going on right here. Okay, so the accuracy of the model is going to be computed the following way. We need to look at the people who are actually yes, who are predicted to be yes. So these are the people who are actually yes, who are predicted to be yes. The accuracy of the model is 140 over 200. So the model has a 70% accuracy. But you know what's funny? What is the accuracy of the naive model? So what is the accuracy of the naive model? 100,000 points, all those answers. Thank you for everyone answering. This is some real learning right here. And we'll end right at 2. If anyone has to leave at any point, feel free to leave. Remember, it is recorded. Sorry, I started a tiny bit late. What is the accuracy of the naive model? Does anyone know? This is on the homework. And if we use the naive model, and John is right, the accuracy of the naive model does not know about these predictions. Predictions are made from X variables. So predictions are made from X variables. Remember that predictions are made from X variables. So the naive model would only know what things actually are. So the naive model would predict everyone is yes, and the naive model actually does pretty well. The naive model only does a little bit worse than the actual model. So who knows what happens when we put this to new data, because maybe our models overfit and maybe the naive model is like, well, let's just predict everyone's going to donate instead of using a model that tells us who's going to donate because maybe the model does worse. So like on new data. So yep, you got it. The naive model would only know this. Great job, Julio. 100,000 points. I love seeing 201s in here following along. This is and if you look, remember what it said and you got it. All we're using here, Connor, 100,000 points, is we're using the marginal probability. Do you see how right here it says marginal probability? And look over here, the probability in the margins. So this is the marginal distribution of what people actually donated. And then we use the majority level, as Connor says right there. Because if most people donated, then what would you predict? Random person. I would predict they donated. So the naive model uses the majority level. And once again, it doesn't use predictions because predictions come from X's. And to make predictions, we need those X's, but the naive has no X's. So the naive is just like, well, I only know the Y variable, so let's use what things actually are. Big concept right there, that the naive model uses only what Y is and uses the majority level. So the naive model only uses the majority level of y, and that's it. Posterior probability is after some information. If you look at the probability of A, where we have the probability of A given B, this is the probability A given B. So it's after we have information. It's like knowing somebody was an engineer, then what's the probability of them donating now? So posterior distributions give us new information and help us predict better. So that's our goal right here, is to make better and better and better predictions. So we have right here, Jane is a 42-year-old single mother of two. Kids are 10 and 13, who works 40 hours. She works in an investment firm. She has been a customer of Verizon for 8 years, yada, yada, yada. So what would the prior probability be? Can someone explain in words? I want to have you guys write answers. Can someone explain in words what the prior probability would be here? What would the prior probability be of her churning? Churning means to leave your cell phone provider. What would it be? And I might just say it so we can make sure we got 15 more minutes, and I want to make sure we get through as much as we can today. The prior probability would simply be the probability anyone leaves. That's because we're not going to take into account this information. The posterior is given the information. These are key words right here. That the prior probability would just be, well, what's the probability anyone churns? Does everyone understand that concept? That the prior probability for Jane churning does not take into account her information. That's called the posterior probability. Think of it like posterior, like afterwards. So when you have the prior probability, it's simply what is the probability of anybody churning? Because we're not going to use her information. But the posterior is, and what would be the naive model most likely? If maybe we lose 30% of our customers, the probability of her churning would be 30%. Kyle, 10,000 points still though. So it would be whatever the probability is that people leave our cell phone company. That would be the prior probability, because we're not going to use any information about her. We're just going to be like, what's the probability someone leaves? 30%? Sure, 30% for her too. But then, or for this person, because we don't know anything about her. But then when we talk about the posterior, we're going to use all this information to say, given this information, then what is the probability she leaves? So that's the key right there, that the posterior would calculate that way. So there's only one Jane right here. That's the problem with a lot of what we're doing, like all these assumptions we have in statistics. So we really get into these problems that she's a very unique individual, and we could get a big kind of like error on her. And that's why we oftentimes see that our model might overfit, especially with taking into account age, marital status, kids, jobs, salary, subscription history. We'll probably be overfitting, because if Jane leaves and she's the one person like herself, we might just be predicting everyone like Jane leaves, but we're only basing our model off one prediction. That is so huge right there. Please listen in closely, because as I say these things, all I hear in my head is overfitting, overfitting, overfitting. Because remember, overfitting occurs when we overlearn information about the data in our model. So if you only have one Jane, and then she has all these unique characteristics, and then you learn all these characteristics about her and make a model from it. So good to see you, Colin. Thank you very much. I am. And if you overlearn all these characteristics about her, then your model has completely overfit. You're now mod, Colin. So your model has completely overfit to the data if it learns all that information about her too much. And then it will not generalize to new data, because you're basing your model off one person. And this goes for multiple people throughout the model. Maybe there is a Brian in the model, and the Brian is unique in and of himself. But if we learn all these characteristics about Brian, then it's going to overlearn Brian and say, well, everyone's going to act like Brian. So do not put too many variables in your model, which sounds so counterintuitive. Like, wait, don't put too many variables? Don't do that? It's like, what can you do? We've got right here a calculation of the margin of error. We rarely ever do this, but this is the way to calculate the margin of error. We won't be putting this on the test. I'll make sure we won't. Let's get into some logistic regression right here. We've got through a good bit of slides today, but there's a lot of material. Logistic regression, and its interpretation. Okay, here we go. Remember, we front load ourselves. We talk about a lot of key concepts to make sure when we get to the slides, we already know them. So, logistic is used for what types of variables? I need to hear this again. I can't have you guys repeat this enough. should know it like this: 100,000 points first person to tell me, 10,000 points everyone else. You have to know logistic is this. Connor's right. He's got it. It is for categorical variables right there. Joelle gets the full. She gets 100,000 times the full thing. So Joelle and Connor both get the 100,000. Everyone else gets the 10,000. You need to know it's for categorical variables. Now, there is such a thing as multinomial logistic. We are not doing multinomial logistic. Multinomial logistic, when you think of multinomial, that means multiple level. So there is a way to do multiple level classification, multinomial logistic. There's packages for it, but we're not doing that currently. We're just doing 2-level classification with logistic regression. So once again, my brain turned on and I remembered that logistic, the level of interest, is last. Once again, as I keep saying, we're front loading ourselves with a lot of knowledge. So don't just go to the slide. Remember, watch the whole lecture as we do these things, because we should know our saying. 100,000 points again in the chat. I know I'm throwing crazy points, but I want you guys to be interacting all throughout the lecture. I want you to say my favorite sentence right here, that in logistic, what? In logistic, what? We should know it. We should know the logistic what. You'll see someone type it. Logistic what? What is it? Logistic, the whole thing. People are kind of saying it. Logistic last. Logistic is last. Level of interest is last in logistic. Listen to all those L's. Listen to the alliteration of it. In logistic, the level of interest is last. If you remember earlier, and I didn't do it as like a fake thing, I had to stop and think. I had to be like, wait a minute. Is it first or last? And I was like, okay, wait a minute. And then my brain was like, oh yeah, logistic level of interest is last. And then I did a check on it. You can always look at the output because the output will show you it. Exactly. I love it. Everyone earned the points. In logistic, the level of interest is last. And what is the level of interest? It is the level we are predicting. So the level we are predicting could be like yes or no, and we'd predict yes. Now, once again, what if you want no? Well, it's just the complement. You'll see it right there. I can almost point to it. There it is over there. It's right next to me over there. The complement, that's all it is. The complement of yes is no. And you'd be like, wait a minute, it's not yes. Because what about maybe? Well, we're doing 2 levels here. So since we're only doing 2 levels, the complement of one level is the other level. So since it's only 2 levels, you can't be like, well, what about, because in 201 we learn yes has the complement of not yes. So you either say yes or not yes. But in 2 level, we would say, something's either junk or spam. So you could say junk or not junk. But since it's 2 level, it's either that level or it's not that level. So there we go. Fun stuff on that. The probabilities output are discussed are the posterior probabilities. So when you heard me talking about the posterior probabilities just a moment ago, all of those probabilities that we are outputting right there, let's go to the curve we drew a while ago. Here it is. Oops, I thought I had it up. So right here, the probability of yes being output by this model is the posterior probability. This up there is the posterior probability. Now, the prior probability could be something like this. And we said this earlier. That is the marginal that is the marginal probability of yes, as in like 55% of the population said yes. So this right here is the prior probability, and that's not the line that Petrie put in, but that's like the prior probability and then the posterior. So everyone would be predicted to have a 55 probability of being yes, and if people have a 55% probability of being yes, what would you predict for them? You'd predict yes. If people have a 55% probability of being predicted yes or being yes, then you would predict they are yes. I mean, it's like you have a 55% chance of donating. Well, I predict you'll donate. But then the posterior model is the actual logistic curve. The posterior model is the actual curve, which gives us usually better predictions, we would hope. Here's what I just said. Awesome. Once again, when you get your probabilities, is this highlighter? Oh, there we go. There we go. Now we got some stuff going on. So when you get your probabilities right here, if you get a probability of 0.5 or higher, and I will say this, R a lot of times will flip a coin on the 0.5, so don't worry about it. If you're doing it, you can just say it is the level of interest. But if we get a probability prediction of 0.5 or higher, we predict something is the level of interest. If it's 0.5, lower than 0.5, we predict it's not. As in this model right here, and let's change, if this is the 0.5 line, then all of these individuals are going to be predicted no, and all of these individuals are going to be predicted yes. That is how the model works. The model predicts whether something is or is not going to donate, but the prior model is going to predict everything. Can we still have physical office hours if we... they don't want no students on campus. I know, such a bummer, right? They want no students on campus, and I gotta get stuff out of my office. So you might see me like running, be like, "Hey, Brian," I'll be like, "Hey." We'll finish up here. We got a few more slides, but if you notice how much we front loaded it, we're gonna go right till 2, and then we'll end immediately. So sorry, I know we lost 5 minutes at the start, and I know it's the end of class right now. If you have to leave at any point, just tell me. But I'm just gonna go through a few bit more slides here. Once again, you notice, what do we have? I want to see it in the chat. Have you already seen this equation today? Yes or no? Have you seen that equation today? Have I shown you this equation? Have we? Yes, we have. Yes, we have. We've talked through this equation. We've talked through the implications of it. We're always front-loading our knowledge by talking about these things because we're not just going to read slides. This is the logistic equation, and we know how it works. We understand that it is just the regression equation, and we use it to predict a probability. And then we also understand that it can be multiple logistic. Multiple logistic, and we talked through this a lot earlier, that multiple logistic is just going to be, and here we are, just increasing the number of variables being used. So if you're like, wait, we didn't get through enough slides, I promise you, we've been covering a lot more today than we have with the slides because I do the concepts as they kind of come. I don't want to just be like, well, let's not talk about that. Let's talk about every one of these in depth. So we have definitely talked about how the equation works, and as this is the regression equation right here. Yep, we will have class next week, and I'll be releasing schedules this weekend on how everything goes. Let me see here. We might just do like 1 or 2 more slides here. There's a positive logistic, there's a negative logistic, and then we'll do this. We'll do this idea about, cool, that's interpretations. Okay, we'll do this right here, and then we'll end, and I'll take questions. So the biggest thing to know is how logistic works. Logistics, and we might do, I don't know, if you guys want Zoom, I might do Zoom, and then we might try to do this too. If you guys want personal office hours, like if you guys want to meet personally, but then I like recording these and putting these out there so everyone can watch them too. We will do lab tomorrow. I'll be posting the lab tomorrow. And I'll say this real briefly here. Logistic regression can be used in many ways, but the way logistic is generally used is a monotonic increase. But Dr. Petrie updated from the 320 to 474 slides where you can do crazy things, where you can throw in interactions or polynomials and stuff like this and actually get logistics, I can't highlight it or I can't draw on it yet, to do non-monotonic shapes. If you look, there's a polynomial in there, and that actually creates a non-monotonic shape. So there are ways using multiple logistics to do all this. And then I'm going to I'll send out a time layer tonight. I will post like when I'm doing it. And so you guys will have a video of me doing the lab, talking through it, and doing more concepts to make sure everyone's on track. Sorry we missed Tuesday, a lot of setup and everything, but I think that's got it. I think that's the last I want to talk about with this right here. And that puts us at a good spot right here because now we're into interpretations and then kind of looking at models. We don't do much with maximum likelihoods. Naive model. We talked about confusion matrix. That one's got predicted on the other side. Sorry, I put it on the other side of mine today. There's Kappa right there. The accuracy of our model versus the random model. There's the one. So we've done a lot of concepts today, false positive, false negatives. All future labs going to be outside of our... Nope. We're going to try to do... Sorry, I lost a class. So Elliot, great question. Future labs will be during regular class time. So I'm just kind of making up for Tuesday. So thank you everyone for kind of putting up with me not being here on Tuesday. And I really appreciate that. Other questions you have right now, feel free to ask. But we covered a lot of different things today. And I put my... actual on the other side. I don't use sensitivity and specificity. There's the ROC curve. We covered that today. That's a pretty good ROC curve. Pretty good. And there's an amazing ROC curve. Look at that ROC. Literally, if we could put this on the test and say, what do you believe the ROC curve is right here? And you'd have to say it's very close to 1. All this good stuff. Will there be ways for us to look at the exams? I think I might be able to scan them. Maybe I'll just scan all of them. So I And we're going to be very nice on the, like, we're going to be generous on the curves and everything. So I'm going to try to find ways to do this. It sucks, like, trying to avoid everybody. So I'm so sorry. I know it's, like, craziness, but we're going to be really, really nice on, like, and then, like, yeah, I think, because, John, we're going to work on yours tomorrow. So probably tomorrow we're going to go and do that. And in logistic, would the curve be split if we use categorical? Yes. If you use categorical predictors in your logistic, the visualization, if you use categorical variables, like, you will get the following. Like, if you have one quantitative X and and a quantitative Y and one categorical X, you get like a curve here, and you'll get a curve here. And that's with like no interaction. I drew that second curve incorrectly. It should be follow the same curve. And so you'll get like level yes and level no. And so that'll be the categorical variable. So and I get every answer right here. Copy that. There you go. And so we'll set up a time tomorrow. John knows one more person. How will coding night work? We're probably doing a take-home exam. So we'll probably have you guys do a take-home exam. Please don't post answers anywhere or ask for help you shouldn't get. But we will do that. And I should be releasing test grades later tonight. We're going to put a nice curve on them. So keep doing your homeworks. Keep doing the labs. Tomorrow I'm going to get online and do the lab and go through more of the concepts. So it'll be very important to watch tomorrow's lecture when you have some time and use it to complete the lab. So I'll be going through a lot more of the concepts tomorrow. So join in. I'll send out reminders tonight about it. But I think that's got it. So so we're going to do like take home. Let's think. I think the labs are due on the weekend. I think we have them do like Sunday night. We push them all back so people could have more time. So that way they wouldn't have to be done during class. We're trying to be as good with everyone's schedules as we can. So let's think. Tomorrow, probably, let's like maybe do like 10 a.m. or something. Does 10 a.m. work in the morning to do like the lab? Does everyone want to kind of do that? We'll do like 10 a.m. And then we will, like, I'll give tests later in the day for people who need the tests. So John, especially, I'll probably do like 10 a.m. sounds good. Okay, so let's plan for 10 a.m. I'll send out an email reminder, and then we'll do later in the day for the people who need to take test. Any other last questions? And thank you so much. I'm glad. Did you guys like this format? Did it work pretty well? Was it pretty able to hear, understand me, and see what's going on? 10 a.m. tomorrow. How long will the lab take? We might do it for like an hour and a half or so. We're going to go, you like it? Awesome. And everything is recorded here. The lab will be recorded tomorrow if you can't come. And it's totally Eastern Standard Time. I'm still in Knoxville. So, yep. Quinlan, thank you so much. I'm so glad to hear that. I'm screenshotting that. Thank you so much. That makes my day right here. I really believe in this format we have that I can do things really easily and I can see what you guys are saying. It's so cool. I've got a 3-screen setup. This is what I want because I can see everything you're seeing here and I can literally look out and see you guys. Like I've got the camera right there. So when I'm looking at you guys, I can see everything. Well, that's got it. I'm going to head over to 201, but Rick and Morty outro, you got it. Oh, wait, we don't have a Rick and Morty outro. We'll play it. Are you ready? Caleb, you guys are awesome. Okay, talk to you guys later. I will see you tomorrow at 10 a.m. We'll always be interaction, and we'll always be interactive, and we'll always be helpful. Rick and Morty outro.
Like TV from other dimensions has a somewhat looser feel to it.
Yeah, it's got an almost improvisational tone.